I'd like to thank everybody for coming today. I know Denny and I are really excited to be here to talk about the Auto ML Toolkit and kind of show an example of what this looks like in a Databricks environment. So again, if you're walking into the room, this is the talk regarding augmenting machine learning with the Databricks Labs Auto ML Toolkit. So we'll start off by talking through the traditional stages of machine learning and a machine learning pipeline and what that looks like kind of at a current state. And then we'll move into talking a little bit about the AutoML Toolkit specifically and how it works to solve these problems, things like hyperparameter optimization, choosing different models, and sort of scaling it to a few best practices. But before we jump in, we'll do quick introductions. So as James said, my name is Mary Grace Moesta. I'm a customer success engineer at Databricks. I'm currently involved in developing some of the AutoML project, as well as I previously was a data scientist where I focused on some machine learning as it pertained to brand accelerator and some customer experience work. I also like long walks on the beach, Spark, and applied math, so it's a really fun combination there.
And hi, okay, here we go. My name is Denny Lee. I'm a developer advocate here at Databricks. I've been working with Apache Spark since 0.5 days. Former senior director of data science engineering at Concur. And you can either blame me or thank me for what is currently known as Azure HD Insight. So.
Awesome. So before we talk and get a little bit more hands-on with the AutoML Toolkit, I think it's important to kind of talk a little bit high level and explain like the way it was designed. So it has a bit of a tiered approach to the APIs, and those tiers kind of map back to different personas that we were seeing in the field. And so the first one is a citizen data scientist, and kind of the goal of their journey is, minimal code, pretty heavy on the automation side of things. And if we kind of make this analogy to vehicles, that's more of a like semi-autonomous vehicle sort of analogy. And so the way that AutoML can kind of appeal to this persona is through the high-level APIs, specifically through the automation runner, which is what we'll walk through in a few minutes. And then working down that list there, the engineers. So those folks kind of tend to have, want a little bit more hands-on with the code, a little bit more low-level augmentation. And so that's where those mid-level APIs come in through the individual components. And again, if we're reverting back to this driving analogy, that's more of an automatic transmission type metaphor. And lastly, those machine learning experts, those researchers, those folks who want to be knee-deep in code, be able to pull every lever possible, and have as much control over their machine learning pipeline as possible, that's where those low-level APIs come in, and it comes helpful for hyperparameter tuning. And again, when we're thinking about that driving analogy, it's going to be a manual transmission. So by no means are these mutually exclusive. There's obviously a lot of ebb and flow across them, but we'll kind of be reverting back to the different levels of the APIs as we go through and talk through the examples. So let's do something very makes a lot of sense. Let's start at the end. And so when we're looking at the machine pipeline as a whole, what we'll focus on today is really that phase of identifying features to put into your model, and then the actual model training part. So the tuning, the building, and then executing and reviewing the metrics using MLflow. So we'll focus on, again, like those kind of main parts today as we move through. And again, the structure is we'll kind of say, okay, here's what the current state looks like if you're building a model by hand without the AutoML Toolkit, and then we'll compare it directly to, okay, how does this look in the AutoML Toolkit? So like I said, we'll go through the feature importances module, and this module helps automate the discovery of features to make sure that, as you're building your models, you're putting in features that truly matter and that are going to be very indicative of predicting your dependent variable. And we'll talk about the automation runner. So again, that's going to be in reference to those higher level APIs that I spoke of. And so how that helps automate the building, training, execution, and tuning of a model. And then we actually apply this to a data set, to the loan data set. And so we actually were able to improve the area under the curve from 0.67 to 0.72. And a lot of this, like, really in-depth, these details are really cool and interesting to talk about. But if we look at it from a higher level perspective, we were able to kind of adjust the business value by increasing that AUC from a $23 million savings to about $68 million. And ultimately, we were able to do it with less code and faster. So like I said, we're going to kind of kick it off by talking through the feature importances. And so if we're thinking about the machine learning process, this comes after the feature engineering step. So you've built all your features, and now it's time to discern, okay, which ones are going to be important for me to put into my machine learning model. And so when you're doing this in a traditional machine learning pipeline, there's a lot of exploratory analysis that has to be done. So we actually are going to be flipping kind of back between notebooks and the presentation here. But so this notebook, again, like not going to spend too much time on the code, but essentially we've loaded in a data set, and now it's time to say, okay, which ones are really going to matter. So we go through and do some plot some distributions, some partial dependence using correlations, and do a ton of EDA, right, to say, okay, which ones are going to be worth it for me to investigate. Moral of the story is that's a lengthy process, right? It's manual. You kind of got to be very intent when you're doing this analysis. But when you're doing this in the AutoML Toolkit, you actually can use this feature importances module that I've alluded to a few times now. So what this looks like in the code, again, this is like the screenshot of the code. We'll jump into the notebook. We've kind of loaded in the packages. We've set up our data set. And this is, again, kind of what we're looking at. So it's the loan data set. We've got a various set of features here, including things like annual income, credit length, all that stuff like that. And so we'll be predicting this label column. We'll be predicting this 0-1 outcome of defaulting on the loan or not. And so as we start to configure the AutoML Toolkit, we'll go through those maps in a second. This is what that feature importance code looks like. So we'll actually be able to run this in real time. And you'll see that as this kicks off, the logs actually start to print out and give you a little bit more insight as to what's happening under the hood. So as this process begins to execute, you have a lot of visibility into, okay, what's really happening? I'm going to get an output of this, but how is calculating this output? You'll be able to see, okay, it's testing all of these hyperparameters, this alpha value, this ETA, this gamma value, to go ahead and pick the optimal feature importances. So we'll see that this actually takes about a minute to run, and that's because Denny kind of has beefed up our cluster significantly. And so this is running on Databricks, right? So it's running on Spark. And that's one of the powers of the AutoML Toolkit, is that you can run it in a distributed fashion. And so when it comes to sizing up the cluster, right, Denny was able to do some testing of different sets of clusters and how long things took. So you'll see we've got a little bit of chart that kind of speaks to this performance a little bit, but I'll kind of let Denny take it over and talk to it specifically.
Cool, thanks. And so the quick context is that when we start off with a compute-heavy resource, this is AWS instances, but you can obviously use Azure instances, but that's why you see C4s. So we start off with C4s just to see how well it would run. And you notice that basically with 4 nodes, and so running the exact same feature importance, in this case it was XGBoost, took about 7.5 minutes. But basically, we added more nodes to see if we could get the processing down faster. Because don't forget, what happens is that all the different hyperparameter combinations that we're trying, we're actually going to go ahead and send them out to multiple different nodes, right? So the more nodes you have, the faster I can go ahead and complete all this. So once I got to 8, all right, almost half, sweet. But then when I went to 12, basically nothing happened. It was because I basically saturated the driver, and I wasn't actually able to go ahead and improve the efficiency of the worker nodes at all. So what we did is that we actually knocked them up to C5s. These are much faster CPUs and GPUs underneath the covers. And so because I got the faster compute nodes, basically now we knocked it down to 1.96 minutes at 8 nodes. And also we had a large enough driver so we could actually saturate it, because what happens is if you're trying to run that many jobs concurrently, right, you basically will saturate the driver to the point of it collapsing. So we basically didn't want to do that, so we put a larger driver. So ultimately, the context is the more complicated, the more data you have, more complicated it is. The potentially larger you want to get the faster compute instances, and the larger the nodes you want in order to be able to go ahead and handle it. That's basically what it comes down to. And because for the purpose of this demo, we also shrunk down the data size. So we actually have both the original data set notebooks that we'll be releasing, as well as the sample ones. The sample ones allows us to finish the demos in time for this presentation. The actual full data set and the actual full ones took about 10 minutes to run, but we just figured that was too long for demo purposes. So, yeah.
Awesome. So if we look at the output of the feature importance, we'll see we've got a few features and their rank of importance. So based off of those importances, we can go ahead and select them and identify those as our selection fields, as our important features that we're going to put into our model in the next step. So just to kind of review a little bit, we were able to kind of take some of that EDA and take some of that feature exploration that we were doing when we were building a model by hand and turn that into a few lines of code to generate a list of features that we're going to use in our model. We'll go through a little bit more of the specifics. You'll see some things on here that we haven't necessarily addressed yet. We will talk about that in just a couple minutes. So again, it outputs, one of the outputs is a data frame where you can then extract those features to push into your model.
And just as a quick note, the reason it's different is because this is for the full data set. That's why the numbers look different. And the sample data set looks a little bit different because we shrunk the size massively. So that's why it's slightly different. Just to give you context.
So now if we're looking at a process from the whole, we've engineered our features, we've selected the important ones that we want to push into our model. Now let's actually get to the steps where we're building, executing, tuning, and then reviewing the metrics of several different models. And so what this looks like in a traditional model building and tuning pipeline is it's a little bit overwhelming looking at it on the slide there. But there is a lot of sort of ifs, ands, and buts that has to happen to actually build out your features and build out your model and start to tune it. So you have to make sure that you're on top of things like numeric columns, categorical columns, setting out, okay, what's going to be my threshold for categorical versus numerical values, wrapping it together in a pipeline, string indexing, one-hot encoding. There's an endless list of things I could start to talk about here. And from a code perspective, you'll see that these little screenshots posted on the far right side of the screen, this is kind of what it looks like from a code perspective, right? Very, laborious, pretty intensive when it comes to just making sure that you fine-tune all these tiny, tiny details. So then it comes to building out your model and then executing it on your data set, and then you're reviewing those metrics. In this case, we're speaking specifically to AUC, but again, that differs depending on regressor or classifier. So long story short, I'm sure everyone in this room is really aware, this process is really labor intensive. And so the question that we hope to answer through this AutoML toolkit is, okay, how do we make this easier? And so this is kind of what it looks like in the AutoML world. That's where the automation runner comes in. So again, as I spoke to before, the design was to have these tiered APIs. And so the automation runner is a means towards having, just like it says, a lot of automation pretty hands-off of the code. So you can go ahead and use the automation runner, use all the defaults, and run a model if you don't want to have all these levers be pulled. So this is kind of what it looks like from a code perspective. So again, thinking about the comparison here, we've got those lines and lines of code that it took to build and tune our XGBoost model in our handmade process versus what it looks like in AutoML. So we'll jump back to the notebook here. And so again, we've kind of selected our important features, and now we want to kick off our automation runner. So we set the modeling type. Again, sometimes this is referred to as a model family, and also the type, so regressor versus classifier. We do a little bit with some of the overrides and configs, which again, that's kind of going to be the way that we're jumping across the different tiers of the APIs, which I'll dive a little bit deeper into later. But we'll go ahead and kick this guy off. And very much like the feature importance runner, you'll see that it prints out, and you have a little bit of insight as to what's really happening under the hood. So it prints out all of the configs. So there's several configs that can be set depending on the model family and type. And so if we look into these a little bit, we'll see we've got the configs listed, and then it starts to go ahead and tune our hyperparameters. So again, very much like the feature importance runner, we'll see that we've got all these hyperparameter values that we're testing, different alphas, different ETAs, different gammas, things like that, to say, okay, what's gonna optimize our measure of variance. And so again, this is an instance where this beefed up cluster really comes in handy because this will only take a couple minutes to run. And so if we're, again, comparing head-to-head, we've been able to condense this modeling process into just a few lines of code that we'll talk a little bit more in depth about. So as we run this, part of the AutoML toolkit is that it automatically logs to MLflow. So when it comes to that part of reviewing your metrics, that's going to be logged for you in MLflow. And so what this looks like is, again, this is a screenshot, but I've got it pulled up, is you've got your instance, your inference config. So again, this is going to be the tag that has all of your configs in it. And you also got some other useful information that sits in here. So you don't have to worry about configuring MLflow. It is configured within those configs. You do have to set up, the experiment name and things like that. But as it runs all these hyperparameter runs, it logs everything to MLflow. So you can go ahead and track it and select your best model after your automation runner has run. And so compared to our handmade model, we actually increased the area under the curve by about 5%. And so before we jump into kind of looking at this from a higher level of how did AutoML Toolkit do this better, I want to jump back to the notebook and talk a little bit more in depth about some of the configs. So some of the things I did some hand waving over earlier, you'll see that this generic map overrides is something that's a parameter for both the feature importance config and our automation runner. And so I think the natural question is, OK, what is that? And so again, this is kind of the means that you can use to jump between the different tiers of the APIs. So if you're using the automation runner, you can do automation runner, set your model family model type, .run, and you're good to go using all the defaults. The defaults have been set very intentionally so that users who don't want to play around with them very much can have very little touch and run a model successfully. But say you want a little bit more control, right? You want to better tune your model for your business case. That's where you can modify those configs yourself. So you'll see there's a ton of them here. There's more that aren't listed. And again, these differ depending on the model family and model type. So in this case, we modified some of the configs. And again, I'm not going to go through them all. They're kind of all documented on GitHub. But again, this is the lever that you can pull if you want more control, right? So if you want to be that ML researcher, that experimenter that's knee-deep in code and wants to fine-tune everything, you have the ability to do that. But at the same time, if you fall or identify more with that citizen data scientist persona, you can use the automation runner.run and you're off to the races. So if we think about the process comparing the AutoML Toolkit to a handmade XGBoost model, how did AutoML do this better? It kind of in three main ways, right? So we were able to test and tune all modifiable hyperparameters. Whether you set those in the configs or whether you use the defaults, it goes ahead and runs that all for you. It runs on Spark, right? So it's performing this in a distributed manner using a collection of optimization algorithms, especially on Databricks. You'll get some great performance. And then it also, when it's hyperparameter tuning, it incorporates an understanding of how the parameters were extracted from the algorithm before. So it uses a genetic algorithm of parents and futures to basically better tune your hyperparameters. So like I said, there's a vast list of configurations that you can set and that are set for you. But these are just kind of some common overrides that are kind of recommended moving forward. So the first one is the data prep cache. And so this is going to cache your primary data frame for faster batch processing. So you won't have to create it every time. It will be cached in memory. So again, you can easily pull that quick. The second one is tuner parallelism. This is more of a Spark config. So it's basically tuning how many workflows run in parallel. And again, kind of like Denny mentioned, this is something that you want to keep an eye on, especially if you have over 30 parallel tasks happening. You're going to oversaturate your driver and kind of run into issues. So that's something that you can kind of, again, another lever you can pull, but there's a little bit of guardrails on that set. The next one is train split method. So in some of the EDA of this loan data set that we explored earlier, we saw that there was a pretty significant class imbalance. And so we wouldn't want to do random sampling. We want to move towards something more like stratified sampling that's going to account for that class imbalance. And so you can use this train split method to adjust your sampling method. The next one is tuner train portion. This is just allowing you to configure your percentages for test and split. I think the default is 80-20, but again, it's something really common that data scientists have preference over. And the next one is the tuner auto stopping score. So this is going to be a value that's going to stop your hyperparameter tuning. So saying, hey, if the AUC hits X value, stop where you are. That's going to be the best model. And so that's also kind of another guardrail to, especially if you're limited on time, you can set that auto stopping score to make sure you're stopping at a reasonable AUC. So again, if we're kind of starting to abstract away from the code a little bit and talk more about the business value and the context that this model was used with, we ran our automation runner and we ran it with the confusion report. So that means it's going to generate a confusion matrix to compare the handmade model versus the AutoML model. So you can see here that not only did we increase the AUC, but we also adjusted those values for the type 1 and type 2 errors. And so what that actually means in the business context, right? So we're talking about loans here. So if we're predicting a 1 and the label is 1, that means we've avoided loss, right? That's good, our prediction's right. If we've predicted 1 and the label is 0, that means we've kind of forfeited profit that we could have had if we had an accurate prediction. Again, if the prediction is 0 and the label is 1, that means we're incurring a loss from that loan. And then if prediction 0 and label 0, we're good to go, we predicted correctly. So when it starts to, the question of quantifying the business value of this, like, yeah, we increase the AUC, that's great, but what does this look like in the business? What is this going to look like to my manager and the people that really are driven by business value? We started to quantify that by the opposite of the loss avoided minus the profit forfeited. And so what that looks like in actual numbers is, with the hand-built XGBoost model, there was a potential savings of $23.22 million. But using the AutoML Toolkit and using the optimizations and hyperparameter tuning that are built into the toolkit, we were able to bump up that savings to something almost close to $69 million. So you can see that not only does this function a little bit better from a code perspective, but as you start to abstract it up to the business value, you do see some significant improvements as well. As we move away from the automation runner, there's kind of another module that can be used to run several models at one time. It's called the FamilyRunner. So Denny made this slide, so there's a little bit of humor in that one. So if we're thinking about the traditional model building experience, in the original blog post that Denny wrote, they actually tried GLM, GBT, and XGBoost. So if we think about that traditional model building process that we outlined a little bit earlier, multiply that by 3, and that's the same process you'll have to go through if you're coming at this from a traditional model building perspective. Long story short, that's a lot of work, right? And so the question is, can you make this easier? The answer is yes, using the AutoML Toolkit. And so there is a family runner that sits in the AutoML Toolkit where you can run, just like it says, a family of models. So very much like the automation runner, you set your model type, or model family rather, and type, regressor classifier, and then you pass through those configs. So again, whether you pass through just a couple overrides or a full list of overrides, you have that control. You can set up all of your configs for your 3 different families of models, and then use the family runner to execute on your source data and pass through the array of varying configs, the config for your random forest, the config for your GBT, and the config for your gradient or XGBoost model, and it will run all those in parallel. And again, it has the same approach as the family runner, right? It works the same way under the hood, except now you're running 3 model families instead of 1. So time is going to be obviously increased in this one, but again, you're encompassing that process that took 3 times as long before, now doesn't take 3 times as long from a code perspective. So we're able to condense lines and lines of code into just a few. And so when it comes to comparing them, like I said, everything's logged in MLflow. And so this is just kind of a visual that's generated that maps out the different models, how they performed, and the different hyperparameters that were tuned to get that performance. So let's end at the end. To kind of recap, from the model building experience, the feature importances automates feature discovery, takes a lot of some of the EDA out of the monotony of data science work. We have the automation runner, and so that is the module that's going to help build, train, execute, and tune your machine learning pipeline, and also helps review metrics, right? Because it's all logging to MLflow. And then we talked a little bit about the family runner, and that helps automate the process of building several different families of machine learning models all at one time. And then when we kind of compared the AutoML Toolkit to just a hand-built XGBoost model, we were able to see like a 5% increase in the area under the curve, which translated to a significant amount of dollar savings to the business context. And ultimately, it had less code and ran significantly faster. So the goal was to kind of make the process easier, and this was our interpretation in how to do it through the AutoML Toolkit. So the roadmap, a little bit about Databricks Labs and the AutoML Toolkit. It is a product that's managed by the field. So folks like myself and other folks at Databricks that work in the field, we're the folks that own it and continually develop on it. So in the 0.6 release, they're targeting to have serialized model and featurization stored, so being able to use the whole Spark ML pipeline in AutoML. They've added a binary encoder and Euclidean distance optimizer for post-modeling search, so adjusting the way that they're searching for hyperparameters. Advanced MBO search for the genetic algorithm that AutoML uses, as well as automated ML flow logging and configuration. So the config set right now is you have to put in like the workspace and your user profile and where you want to log your experiment. But with the 0.6 release, that will be automated, so you'll take that complexity out. As well as a couple bug fixes. And then in the 0.6 release, there will be a Python API, an mleap artifact export, and light GPM support. So that's kind of the ideal roadmap, right? And again, this is something that's managed by the field, so timelines here are a little bit flexible. But that's kind of the content that we had for today. We just kind of wanted to walk through and show the process at a high level. So appreciate everybody for coming. And I'd like to, happy to open the floor to questions if there are any.
If you please raise your hand and I'll run the mic to you for any questions.
Hey, thanks for the talk. I just wanted to ask a question on the hyperparameter optimization.
Mm-hmm.
So when you're running that concurrently, is that a synchronous process, or are you trying to do the asynchronous sort of trial running during that process?
Can you say that again? I'm sorry.
So for hyperparameter optimization,
Mm-hmm.
when you're distributing that process, is that a synchronous process, or are you doing asynchronous optimization?
I think it's async.
Yeah, it's async. So basically what happens is the driver's spinning off multiple tasks, and so you have multiple workers basically throwing everything out there. Because we're logging everything into ML Flow, and we're also logging as much of the inference information into a data frame, we can basically we can persist it in memory nevertheless, but then be able to grab it back when we need to update the information. Right now, if you noticed, hidden inside that gigantic generic overrides. Again, you don't normally have to do that. I'm just saying that's the one we just showcased. There's the best only. That just was specifying that we only logged the best model. If we actually wanted to, we could have logged actually literally every single trial. It's just that then the ML flow thing would have been really big. So
Super long,
yeah, so we didn't want to do that, at least for demo purposes. In actual reality, when you're running it, you actually probably do want to record it, because just because it's the best model like for that situation. For example, in the case of our data sizes, yeah, I can guarantee you the models that we have for the small size are definitely not applicable to the real size. So, yeah.
Hi, is there a model selection automation in this platform?
Nope, so you still have to specify the model family and type.
Yeah, and part of the reason why, by the way, just to give you some context, is because there are various tools out there that try to basically auto-choose. The problem is that more times than not, if you don't know what you're choosing, what you interpret as the results end up going sideways. And so, for example, one of the things we saw early on was to see people actually mixing classifiers with regressors. So yeah, that's just not going to work. So just things like that. So that's part of the reason why, again, because she and her team are actually using this with customers in real time. So yeah, they need both that ability to automate the distribution, yet also at the exact same time be able to know what the heck it's saying. So yeah.
Hi, thank you for your speech. Are you planning to automatically build also model ensembles?
Not currently, that's not on the roadmap, but I mean, like I said, this is a field managed project, so if there's demand from the field, then we can definitely adjust the roadmap accordingly.
Okay, thank you.
Mm-hmm.
Yeah, one thing we forgot to do is we forgot to put the link for the GitHub. So it's actually a GitHub, external GitHub link, so you can actually put issues directly in there to help us prioritize. So.
If there aren't any more questions, round of applause to our presenters today.